Hey everyone, welcome back to Probability Theory. This will be lecture 11 of the course. And in this section, we are going to just do some problems and some examples that sort of span the material covered thus far, so basic probability. So let's go ahead and jump into it. And we'll call this section 1.11, 1.11, Probability, Problems, and Examples. Okay. So let's go ahead and get started. The first example is a sort of combinatorics, kind of counting example. A lot of them are actually. But this involves a deck of cards. And so here I'll just read it out. A standard deck has 52 cards. If you draw 5 cards at random, what's the probability that you get exactly 2 aces? Okay, so you draw 5 cards from a standard deck of cards. What is the probability? What's the probability that you get exactly 2 aces? Okay. All right, well, let's see. So structurally speaking, if you're not familiar with the deck of cards, you probably are, but if you aren't, what's really important here to note is that there are 4 suits in a deck of cards. You got clubs, hearts, spades, and diamonds, and each of those suits has an ace, so 1 ace. And so in total, there are 4 aces in a deck of cards. And so we can start by just kind of thinking about what's the total number of possible outcomes? Right, if I draw 5 cards from a deck, how many different ways are there to do that? It's really just 52, choose 5, isn't it? Right, I'm choosing 5 cards from 52. Right, and so we'll leave that there. That's going to be the denominator. Right, now what we really need to figure out is how many different ways are there to choose exactly 2 aces. And so we call that a favorable outcome. A favorable outcome is choosing 2 aces and 3 other rando cards, non-aces. Okay. And so how many ways are there to choose the aces? Well, I've got 4 total aces, as we said, and I want 2 of them. So there's 4 choose 2 ways to get the aces. I could get an ace of hearts and an ace of diamonds, or I could get an ace of clubs and an ace of hearts. There's 4 different heart aces, so I can pick 2 of them. So there's 4 choose 2 ways to get the aces. And for the remaining 3 cards, what are my options? Well, there's 4 aces in the deck. I don't want the other 3 cards to be an ace, right? So that means I've got 48 non-ace cards, right? So 48 non-ace cards, and I want to select 3 of them, so that's 48 choose 3. So this would be the non-aces. Right, I need 5 total cards. 2 of them need to be aces. The other 3 need to be non-aces, right? And so this is what I'm doing. Okay. Now these selections, right, the aces and the non-aces are totally independent, so we can really just multiply here, can't we? So the favorable outcomes, they number 4 choose 2 times 48 choose 3. Okay, so what do you have? So you really have this thing here divided by this thing here. So this is so once you can kind of visualize how to what the favorable outcomes are versus all of the outcomes, it's really just, then it's, in this case, it's just a combinatorics problem. You got to kind of crunch these numbers and figure out what this amounts to. So the probability that we're interested in is 4 choose 2 times 48, choose 3, all divided by 52, choose 5. Okay, so these are huge numbers, right? 52, choose 5. There's a lot of ways that can. I mean, that's a big number, very big number. And so we're going to use, this stuff. This is where combinatorics comes into play here. So remember, this choose function is, so if you have n choose k, that's equal to n factorial divided by k factorial times n minus k factorial. Okay, so over here, that means you have 4 factorial over 2 factorial 2 factorial times 48 factorial over 3 factorial 45 factorial. That's the numerator. And then the denominator is 52 factorial over 5 factorial 47 factorial, right? So 52 minus 5 is 47. That's where those are coming from. And so let's just invert everything here and kind of combine it all into one expression. So I've got 4 factorial times 48 factorial times 5 factorial times 47 factorial, right? Kind of bringing this denominator here up and putting it in the same, in with these two. And then in the bottom, I've got 2 factorial, 2 factorial, 3 factorial, 45 factorial, and 52 factorial. Okay, so I've got this to clean up. Now this is much easier than it might look because no doubt you will have spent some time recognizing how all these things can simplify, right? But so up top here, I really have the 4 factorial. I'm going to keep that for now. Now instead of the 48 factorial, I'm going to cancel that against the 45 factorial, right? And so when I do that, I basically, all I'm left with is 46 times 47 times 48 in the numerator. Right, so these two will cancel against each other, and this is what I'm left with up top. And I'm going to do something similar here with the 47 and the 52. So the 47 is going to go away, and the 52 will get largely canceled out. So downstairs I still have, let's put the 5 factorial in here too. Okay, so that's everything up top. And then downstairs I've got 2 factorial, 2 factorial, 3 factorial. And then the 52 and the 47, this is where we're going to cancel. So instead of 52 factorial down here, I'm going to have 48 times 49 times 50 times 51 times 52. So everything larger than 47 is still going to be here. Everything else cancels. So I have 48 times 49 times 50 times 51 times 52. Okay, well, the 5 factorial, that's 120. 4 factorial and the 2 factorials will cancel, or you could just explicitly calculate them. 4 times 3 times 2, no problem. But then, you really got to pull out a calculator to figure out what this all is worth. And when you do that, though, you should see 298,874,880 up top. And in the bottom, you've got 7,485,000. Sorry, 485 million. 004, 800. So really big numbers, as I said. And you are going to, when you do that division, you see that that's approximately 0.0399. So we will say it's 4%. Okay, and so if you draw 5 cards at random from a 52 card deck, the probability that you're going to get exactly 2 aces is about 4%. We're close to 4%. Excellent. All right. Next up, another problem here. It's kind of a smaller problem, but not too bad. We roll a pair of 6-sided die. Let y equal the sum of the rolls. Find the probability that y is equal to 9. So this is real similar to the problem we did in last section. So we roll a pair of dice, plural, and we let y be the random variable, be the sum of the rolls. Okay. Find the probability that y is equal to 9. Well, if you want, you can go review that previous lecture, because we had we wrote out the sample space and we translated it into these random variables, into the random variable, which is the sum of the roles. Or you could think about it fresh. You can say, well, okay, the largest number on a die is a 6, and so I can just kind of think through. Okay, I can get a 6 and a 3; those add up to 9. It is also possible to get a 3 and a 6; that adds up to 9. There's nothing else you can do with a 6, so let's go down to 5. Well, I can get a 5 and a 4; those add up to 9, and of course I can get a 4 and a 5; those add up to 9. If I go down to 4, well, the only numbers that add up to 9 would be 4 and a 5, so I already have that. If you go down to 3, the only thing you can add to 3 to get to 9 is the 6, and I already have that. If I go down to 2, then I'm too small. 2 plus 6 is 8, so I can't get to 9. All right, so really these are the only 4 outcomes that will result in the random variable being the sum of the two being equal to 9. And so the total number of roles, total number of outcomes is 6 times 6, the MN rule. Right, and 4 of them result in y equals 9, and so 4 out of 36 is the desired probability, or 1/9, right? Okay, so again, kind of very similar to the one we did in the last section, but good to review these, kind of think about it differently. Let's take a look at another problem. Okay, this one is, so I've got a club with 8 members. A club has 8 members, right? And we'll say 4 women and 4 men. Okay, they need to form a 3-person committee chosen at random. Okay, so I got 8 members total, 4 women, 4 men. I need to form a 3-person committee chosen at random. Right? What's the probability that the committee contains at least 1 woman? What is the probability that the committee contains at least 1 woman? All right. Let's think about this in terms of a random variable. You don't have to do it this way, but let's do it just for practice. Let's let y equal the number of women on the committee. Okay, so what am I interested in? I'm interested in the probability that y is greater than or equal to 1. Okay, well, there's 3 people on the committee, so I'm interested in the probability that y is equal to 1, plus the probability that y is equal to 2, plus the probability that y is equal to 3, right? What I don't want is y equals 0, right? And so this is really the same thing as the probability that y is not equal to 0, which you could think of as 1 minus the probability that y is equal to 0. Right, so you can kind of do this sort of algebra with random variables. You can, just logically express one statement about a random variable in terms of another. Right, so the probability that y is greater than or equal to 1 is equal to the probability that y is not equal to 0, right? Which is equal to 1 minus the probability that y is equal to 0. So this is the way we're going to actually solve this problem. We're going to use this last expression. So let's think about the total number of outcomes. What are the total number of outcomes? Well, I got 8 people, and I'm going to choose 3 of them randomly. That's just 8 choose 3, isn't it? So it's 8 factorial over 3 factorial, 5 factorial. And you can do the math on that, but I believe you will get 56. There's 56 different ways to choose this three-person committee. So again, we're looking for the complement. Basically, we're looking for, we seek the probability that y is equal to 0, right? And what our desired probability is 1 minus this. So we're going to look for this and then subtract it from 1. So we want to find the number of ways to select 3 men, basically from 4 men. So I've got 4 men, and I'm choosing 3 of them. Okay, and so that's just 4 factorial over 3 factorial times 1 factorial. Okay, and of course, you'll see that that's just equal to 4. All right. So now I know this is the desired outcome. Well, it's the converse, the inverse of the complement of the desired outcomes. And then I've got the total number of outcomes here. So what I want here, let's just kind of restate everything. The probability that y is greater than or equal to 1 is equal to 1 minus the probability that y is equal to 0, which is equal to 1 minus 4 over 56. Okay. And if you do that, you get, so 56 minus 4 is 52, so 52 over 56. And I believe that's 13 over 14 if you divide everything by 4, which is 0.929, so approximately 93%. All right, so it's very likely that you'll have at least one woman on the committee. 93% chance, in fact. Right? And that's because you got an equal number of men, equal number of women, and you're randomly selecting 3 from that 8. And yeah, it makes sense. Very good. Alrighty, let's do a couple more. Say 2 or 3 more. 2 more, maybe. What about this example? This is a little more conceptual, perhaps. I've got 5 friends. Okay, I've got Alice, Bob, Clara, Dan, and Emma. Okay, so 5 friends, and these guys are this group is all sitting in a row of 5 chairs. 5 friends: Alice, Bob, Clara, Dan, Emma, A, B, C, D, E, sit in a row of 5 chairs. If they sit randomly, what's the probability that Alice and Bob sit next to each other? Well, what's this look like? All right, so I've got Alice and Bob. Well, let's kind of visualize the events here. So like I got 5 chairs, 1, 2, 3, 4, 5, right? You know, and you could have Alice, Bob, Clara, Dan, Emma. You could have Alice, Clara, Bob, Dan, Emma. You could have Alice, Clara, Dan, Bob, Emma. You know, so there's a lot of them, right? A lot of different ways. Right, and so these are what the events look like. These are like typical events. It's good to visualize these things. There's lots of them. And the events of interest are the ones that have A and B next to each other, right? So this is the event. This is kind of what we're after. So this is the favorable event, we'll say. This is going to be the type of event that's going to go into the numerator of our probability. Right, and so we really need to know the number of events that are like this one here. So we need the number of events that have AB or BA, really, right, in them. Okay, so let's just take this one first, and we know that whatever we get over here, we can just double it because every event that's like this can really be written like this also. So let's just think of the AB style events. So what we can do is we can kind of think of AB as a unit. So think of as a unit, AB as a unit, right? So what do I mean by that? Well, like recast your conception of the events and think of all events as AB being always next to each other. So you've got AB and then C, D, E. Or you have C followed by AB, followed by D, followed by E, right? Right. So think of AB as always being together. Okay. So when we think of it like this, we can really what we're really trying to do is arrange 4 objects. Instead of thinking about arranging 5 objects, we think of A and B as being one of the objects. Okay. And this is straightforward then to enumerate these, right? I've got 4 choices for the first spot, 3 for the second, 2 for the third, and then 1 for the remaining. And so this is really 4 factorial ways. Very simple. Now again, remember, as I said, every time you have an arrangement here, you could also have BA, right? So there's really 2 times 4 factorial ways. Okay, so our favorable outcomes are 2 times 4 factorial ways, which I think 4 factorial is 24, and 2 times that would be 48 total. Okay. And we didn't say this up front, but what's the total number of outcomes? Well, there's, let's go back to your 5 units. So 5 choices, 4 choices, 3 choices, 2 choices, 1 choice. So just 5 factorial, right? So 120. Okay, so the probability of Alice, Bob, Alice, Bob, or Bob, Alice. Well, it's 48 over 120. All right, and I think you get 0.4 when you do that. So about a 40% chance that Alice and Bob will sit next to one another somewhere among the 5 chairs. Alrighty, very good. Let's do another one. This will be kind of a conditional probability type problem. Another card problem. So let's write this out. So given a 52 card deck, you draw 2 cards at random without replacement. Given a 52 card deck, you draw 2 cards at random without replacement. Okay. And what we're interested in is the probability that both cards are face cards given that the first card drawn was. So find the probability that both cards are face cards given that the first card is a face card. Another way to say this is to say, find the probability that the second card is a face card given that the first is a face card. Okay, so we can write this down. What we're looking for is the probability that the second is a face card given the first is a face card. Okay, and then just for simplicity, I'm going to just use the letter A to denote this event, and I'm going to use this to denote, or B to denote the first as a face card. So what we're looking for here is the probability of A given B. Okay, now let's talk about this face card business. So you have 52 cards in a deck and 4 suits. And for each of the suits, you've got a king, a queen, and a jack. Those are the quote-unquote face cards, meaning they've got a face on them. So for each of the 4 suits, you've got 3 face cards. So you have a total of 12 face cards. All right, so that's just information you may need to know in case you didn't. So 12 total face cards. Okay, in case you didn't know that. Okay, and so let's just think about this probability as, as a conditional probability problem. So this is equal to the probability of A and B divided by the probability of B. Okay, so let's think first about the probability of B. All right, the probability of B is the probability that you draw a face card. You've drawn nothing else, you're drawing a face card. So it's simple, right? It's 12 out of 52. There's 12 face cards. I got 52 cards. What's the probability I draw a face card? 12 and 52. Okay, easy. What about the probability of A and B? What's that? Well, the number of ways to draw 2 face cards, right? What is that? So how many ways can I draw 2 face cards? Well, there's 12 face cards in total. I'm going to choose 2 of them. 12, choose 2. Okay, and the number of ways to draw any 2 cards. So remember, we're doing the probability of A and B. So A is a face card, B is a face card. So 12, choose 2 is the numerator, and then in the denominator, I need the total number of ways. Right, so the number of ways to draw 2 cards, of any type, that's the same as the probability of B up here. It's 12 over 52, or 12 over 52, yep. Sorry, no. The number of ways to draw 2 cards is 52, choose 12. Or choose 2, my goodness, sorry about that. Apologies. Okay, so the probability of A and B then is really the number of ways to draw 2 face cards, so 12, choose 2, divided by the number of ways to draw 2 cards of any type, 52, choose 2. Okay. And this is a little combinatorics problem, and so we can work this out. So this would be 12 factorial over 2 factorial times 10 factorial. And we would be dividing that whole thing by 52 factorial over 2 factorial times 50 factorial. Okay, and just kind of organizing this, we get 12 factorial, 2 factorial, 10 factorial times 2 factorial, 50 factorial over 52 factorial. Okay, so you can see you're going to get a lot of cancellation, the 50 and the 52 and the 12 and the 10. And so what you end up, and the 2's these will cancel straight away, so we'll just cross those out. So what you're left with here is 11 times 12. And what you're left with down here is 51 times 52. And so when you do that, you get 0.0498. Okay, so this is the probability of drawing 2 face cards. Now, that's this piece, right? That's this one. Sorry, so coming back up here, we have both of these now. So the probability of A and B is what we just found to be 0.0498. And the probability of B is 12 over 52. Okay, and so we could just plug all that into a calculator. And we see 0.0498 divided by 0.231. And so we get 0.216 as our probability of A given B. Right, and that's intuitive, right? Because we found the probability of drawing 2 face cards is about, 4.9%, about 5%. And this is the probability of drawing a face card given you've just drawn a face card, right? And so it drops, right? I mean, this is the probability of drawing 2 in a row. This is the probability of just drawing one more, given you've already drawn one. So it drops. It makes sense. That's an intuitive answer. Okay, let's just do one more here. This will be another dice rolling experiment. I kind of like this one because it's got a nice little sample space. So 2 6-sided dice are rolled. We roll 2 6-sided dice. Okay. Let's let y be the random variable. Let's define it as the larger of the 2 numbers rolled. Okay, so that's kind of different. It's not a sum, it's not a difference or anything. So for example, I roll a 4 and I roll a 6. Then y is equal to 6. If I roll a 2 and a 1, then y is equal to 2. Right? It's just taking the larger of the 2 rolls and assigning that as y. Okay. So what we're interested in here is what is the probability that y is equal to 4? So we want the probability that y is equal to 4. So the probability that of 4 being the larger of the 2 numbers rolled. Now this is actually kind of complicated if you can't visualize it, right? But I mean, so I roll 2 numbers. What's the probability that the larger of the 2 is 4? Right? So I'm interested in things like this. Right? These are all favorable. But 4 5 is not. And obviously 4 6 is not. Right? Those are kind of out. These are the ones that I want. I want all of the rolls that include a 4 and also include a number less than 4. Okay, so this is one where it's very helpful if you just kind of draw out the sample space. Whenever you have these dice rolling experiments, it's kind of fun to draw the sample space anyway. So 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6, right? So here's my roll 1, roll 2, where they intersect. I'm going to put the value of the random variable. So if I roll a 1 and a 1, then the maximum number rolled is a 1. If I roll a 1 and a 2, then the maximum is 2. A 1 and a 3, the max is 3. A 1 and a 4, the max is 4. A 1 and a 5, the max is 5, and then 6, obviously. So what if I roll a 1 and a 2? If I roll a 1 and a 2, the max is 2. If I roll a 2 and a 2, the max is 2. 2 and 3 becomes 3. 2 and 4 is 4. And then 5 and 6. You can kind of see the pattern starting to emerge here. If I roll a 1 and a 3, the max is 3. A 2 and a 3, the max is 3. A 3 and a 3, the max is 3. And then after that, it's 4, 5, 6. Right? And so you can see that this is going to be 4, 4, 4, 4, 5, and 6. And then 5, 5, 5, 5, 5, and 6. And then, of course, the bottom here is 6, 6, 6, 6, 6. Okay, so you've got your 36 possible outcomes here. And to each of those outcomes, we have assigned a number, namely the larger of the 2 rolls. And so there's 36 total. And we can see that the outcomes of interest are the 4s. Okay, and there are 7 of them. So the probability that y is equal to 4 is 7 out of 36. Okay. All right. Excellent. Okay, so that's where we will leave off. And when we come back in the next section, we're going to get started with, we're going to sort of dig into what are called probability distributions. And we'll start with discrete random variables and their probability distributions. So the class is going to become even more interesting. I think in the next section, I really thought that discrete random variables and their probability distribution is really when this kind of class sort of hits its stride. So until then, take care.